Hello everyone, welcome back to computer organization. So far we have looked at different aspects of computer organization, primarily from the point of view of how we can motivate ourselves to study this subject. We looked at the state of the art. We also looked at some of the interesting things which happened in the evolution of computer. For example, how we from a single core now we are moving into an era of multi-core, etc. We have also started looking into the internals of a computer. We started looking into a very simple computer and the elements inside it, namely we have seen a CPU and what all inside the CPU are there. For example, you have this arithmetic logic unit, the control unit, and then the program counter. And to make a or build a computer, you also need memory where your instructions and data is stored. Now, depending on how this instruction and data memory are organized, you can have different architectures, namely the von Neumann architecture and Harvard architecture, where Harvard architecture says that the instruction and data memory should be separate. Von Neumann architecture says that the memory can be unified for both instruction as well as data. We also looked at that it may not be always a very efficient solution when you have to get everything from the main memory every time you need to execute something. So, since there is high spatial and temporal temporal correlation between the instructions and the data a program accesses, it makes sense to have some small set of registers which are inside the processor itself, and you can basically the data which you are using or you are supposed to use in future or you are very likely to use in future, you can bring it there. So, your execution time can significantly improve. We also looked at how we can design some example ISAs. We looked at one simple ISA where there was only one instruction, and how we can basically write different programs using that single instruction. Now, moving forward, we would like to re-emphasize, and in today's lecture specifically we would like to kind of summarize or basically we would look into the difference between architecture or ISA and organization, and this we will try to do with some interesting analogies, etc. So, in today's lecture we will try to highlight the difference between ISA and organization. Followed by that, we will also look into some key aspects of ISAs. Now, going forward, where we are heading in this course. So, first we will as I mentioned, like we will go little deeper into ISA, different aspects of this ISA, so that we can move very quickly to the assembly level programming, that is what we are planning to explore in near future, and that we will look into from the ISA point of view. So, that if we understand how an instruction set architecture works, and that we can very well relate it with the assembly level coding examples we will look at. In between, we will also try to look into the arithmetic, basically binary arithmetic part, how floating point operations, etc. can be executed. So, we will try to look into that part. After we are done with this, then we will basically start more closely looking into the organization or basically the processor design aspect. So, at the hardware level, what are the design challenges or design consideration we need to take care of, etc. So, that we will spend around 3 weeks or so. So, basically going forward we will look into the computer arithmetic, maybe 1 or 2 weeks on that. ISAs, basically the assembly level coding, we will again planning to spend 3 weeks or so, followed by that processor design, maybe 3 weeks there, and finally we will go little deeper into memory organization, the memory architectures, etc., and there also we plan to spend 3 weeks or so. So, that is how we are planning to organize this course, and further details are already available in the course syllabus. So, feel free to go there and check out the plan for further clarity. All right. So, let me jump on to the content for today. As we discussed that we will be talking about the difference between architecture and organization. Now, the instruction set architecture, or it is also called as simply architecture, sometimes it is called big A architecture also. Books like Hennessy and Patterson mention them as big A architecture. So, they all mean the same thing, instruction set architecture. So, as we have repeatedly or multiple times we have mentioned that architecture is nothing but an abstraction layer, all right. So, it is an abstraction layer which is provided to the programmer or software designer or compiler designer, and this abstraction layer hardly changes. So, basically it is kind of a very settled abstraction layer, not much changes happen there very frequently, and it basically what it does, it theoretically tells how a machine is supposed to execute a program. So, remember that theoretically it tells how a machine is supposed to execute a program. It is not exactly how the machine is going to execute the program, all right. So, what all the ISA contains? So, ISA will give you information about the programmer visible states, for example, how much memory the programmer can plan with, how many registers possibly or whether it has registers, if there are registers, how many of them the programmer can use, so that he can basically think of data reuse and all these things. So, I will come to that part maybe in our subsequent lectures, what do I mean by data reuse. Then ISA also tells about the kind of operations the hardware can do or the machine can do. For example, whether the ISA can handle floating point operation, whether the ISA can handle, let us say, some complicated arithmetic operations like let us say division and so on. So, all these information will be there in the ISA. ISA also provides execution semantics. So, what do I mean by that? So, it means that okay, we know that we know so far that the instructions are written in sequence, the program counter points towards the program or instruction that need to be executed next, and so on. Now, what happens if something happens and the program flow needs to be changed? It can be an interrupt, it can be some kind of a let us say logical operation which or logical condition checking which leads to that change in the sequence of instruction, etc. So, how these things are handled, that is codified in execution semantics. How input output is handled is also defined in the ISA. ISA also defines the kind of data the machine can handle, whether it can handle floating point numbers or it can handle only integers. ISA also talks about the size of the data. For example, whether you will be able to handle a byte, multiple bytes at a time, and so on. All right. So, this is at broad level what is instruction set architecture. Now, if we look at what do we mean by microarchitecture or organization, that is more like the actual implementation of that theoretical description of the machine onto hardware. And while you actually implement it on hardware, you have to have different trade-offs in mind. For example, how whether you want to implement it for best performance, or you would like to implement it for efficiency in terms of energy or maybe cost. So, all these aspects are basically evaluated at the actual microarchitecture implementation, and you will see that many a times there is no single optimal point. For example, if somebody is optimizing things or somebody is basically focusing on speed or performance, then maybe he will find the implementation which is specifically focusing on the performance. Whereas, if somebody is very or some application is very cost conscious, then they will find out an implementation where the cost is of prime importance. And the relevant examples in this microarchitecture or organization can be pipeline depth. So, I know we have not discussed about what is pipeline, but what I will try to do, I will give you an example or analogy, and from there we will try to see this difference, and I hope that many of these terms which we are mentioning here, for example, pipeline depth, number of pipelines, cache size, silicon area. So, all these are physical attributes which are there inside the in the hardware or are related to the hardware, and all these knobs or design decisions at the microarchitecture level will define how whether your solution will be catering to high speed performance, high speed kind of applications, or maybe cost effective implementations or energy efficient implementations, etc. Now, as I have been mentioning, let us look into this through some analogy. Now, the analogy which I thought of sharing with you guys is something which all hopefully can relate to. So, I know many of you or none of you might have visited the campus. Even if you have visited the campus, you might not have accessed the food mess where students get their food, etc. Now, the analogy I would like to present here is related to a student mess. So, let us say for example any mess. So, what is a mess? And the mess is a place where you can go and take food, all right. Now, let us define the architecture or ISA for that mess. So, for any mess, let us say they will have certain kind of protocols. So, let me So, any mess will have certain kind of protocols. So, what those protocols could be? Broadly, the protocols could be, okay, this is a mess where the food is served in counters and it is a buffet kind of system. So, you basically the person comes, takes a plate, takes food and goes and sits and eats, and this keeps on going. Now, what that architecture or ISA for this mess will tell? The architecture or ISA for this mess will be telling us that so I am trying to find out appropriate analogies for the different terminologies mentioned here. So, for example, it will tell about the maximum size, or basically it will give a rough idea about how many students that mess can handle. So, maybe we can relate it with memory. So, let me just try to get the pen. Okay. So, what we are saying that the analogy we are talking about is a mess, and the ISA of the mess will tell us the number of student roughly it can handle. Also, now how efficiently it can handle basically the population, that also for example, how much load, or what will be the typical speed at which the possibly not typical speed. So, basically what I am trying to say is basically the broad ISA level description of a mess will contain the capacity of the mess. The kind of operations the mess can handle. So, the mess can handle, let us say, both veg as well as non-veg kind of food. So, that is also basically defined in the ISA. So, the ISA will say that okay, this mess, whether it can handle veg as well as non-veg food. Now, you think of or try to visualize, if it can handle veg and non-veg, that means you have to have all the precautions or all the arrangements for making sure that veg non-veg do not get mixed up. You have different counters, etc. So, basically all these things should be there. So, but at the ISA level or the architecture level, you will just say that whether veg or non-veg will be able to handle or not. Now, whether the if I come to this and try to find out an appropriate analogy with our example, it can be, let us say, whether the mess has some kind of a fire alarm. So, let us say if there is a fire accident or something, how do you handle it? Do you ask all the people who were there in the mess to be there on the mess itself, or you ask them to leave, and so on. So, these kind of protocols will be defined. So, whether it can handle a fire situation or not, that will be something will be defined as execution semantics of the mess. All right. Now, the analogy for this thing, what kind of input output it can handle. So, I am just again finding some rough analogy. So, do not take it as the face as the actual this thing. So, one possibility of, or one possible analogy can be whether you can basically whether you can allow any outsiders or anybody can walk in and buy coupons and have food in the mess, or it has to be some kind of a predefined list of students who have already paid, etc. So that can be a loose analogy of how do you handle input outputs. Because in program what you are looking at, basically some sensor is giving some input, and from that you are it can be a keyboard, it can be a mouse, and accordingly you are executing something. So basically some external inputs which are not pre-programmed, you are handling them. So these kind of things are, whether it is defined in the ISA or not. Data types and data size. So again, maybe data type can be your basically I would say the kind of food you serve, or yeah, possibly you can mention the kind of food we can serve as data type. Similarly, we can think of size as whether how much let me think about it. So size, I think one interesting example can be, let us say for whom this mess is being designed. Is it for a primary school students? Then the size of serving will be different than the size of serving for a, let us say, college going student, etc. So I do not know whether it makes sense. So but size can be equivalent to, let us say, the size of the plate you provide to the person or student who is coming in the mess. So it can be a big size plate, it can be a small size plate depending on your arrangement. So all these things are defined in your ISA. So essentially what you are saying, that the ISA contains all this information about how this student mess should look like. What could be the actual capacity, whether it has some kind of what kind of food it can serve, whether it can have both veg and non-veg, whether it has fire alarm, whether it can handle, let us say, somebody just walking in for food, what is the size of the plate, what kind of food are being served, basically, or the different types of food being served, like whether it has a single cuisine or there can be multiple cuisines. So yeah, that may be a good example. So whether it has only one cuisine or it has multiple cuisines, like you can have Asian, you can have South Indian, and so on. So all these things are defined as part of ISA. Now they just theoretically talks about how the mess should look like, right, or what are the capabilities of the mess. But if you look at an actual mess, so they might, let us say, an actual mess have can serve both veg, non-veg, can serve or can have all these things. But now how actually it is getting implemented, that is part of your micro architecture. So what do I mean? So now let us say I want to set up a mess and I have limited amount of budget. I have a very small room also to set up this mess. So what I will do, I can still say that I want to serve both veg, non-veg, I want to have fire alarm, I want to have people walking in and have food, and basically yeah, and so on. But since I have a small capacity, what I will do, one extreme case can be, let us say this is my mess, okay, people walk in from here. So basically let us say this is my kitchen area where cooking etc. is being done, and this is the basically a table where food after cooked food is kept. You take your plate from here, walk in this direction, get the food and sit somewhere here and have food, alright. Now because I have a very small setup, what I can do, I can put all the items in the same place and I can allow one person walk in, take food item, all the items, and then basically sit on the table, and then only I allow the next person to come in. So this is a still a valid mess where I am serving both veg, non-veg, I have all the things there, right, whatever I need to I want to have. But this is a very small mess with very little manpower and so on, alright. On the other hand, I can think about a situation where let us say I need, now here the problem is, since I will be only allowing one person at a time, so if I suddenly get too many people, then the queue will be pretty long. So think about it, you went to the mess to have food and basically the food is kept in one plate and there is only one spoon with which you can take all the items. That is why, like, once you have taken all the items, then only the next person can come and take food, alright. So essentially there will be a long queue because one person maybe for taking all the items, he will take maybe let us say approximately 1 minute. So the speed at which you will move, this queue will move is one person per minute, alright. Now I can have a different situation. Let us say here I am not constrained by number of spoons or the table size etc. So what I can do, I can build again a mess where this is my basically the buffet table. Here let us say I have 5 items. So for each item I have a spoon kept there, alright. So a person comes in, he takes this item, he moves to the next one, the next person can come in now, alright. And by the time this next person has taken the food, he will move to the this counter and the person who was here, he will move here and a new person can join the queue and so on. So you see that and assume that still to take all the items it takes still 1 minute, alright. So now think about it. So the first person, he took 1 minute from the moment he entered the queue and he went out of the queue, and the time difference was 1 minute, alright. Let me just switch off this, yeah. So basically the person, first person took 1 minute. Now how long the second person will come out of the queue? The second person will come out of this queue after so this is 5 stages and basically all the 5 stages take 1 minute. So 1/5 of the minute. So after the first person comes out, in 1/5 of the minute, or let us say so 12 seconds. So after 12 seconds the next person will come out of the queue. So in this case I will get one person coming out of the queue, or basically effectively the food will be served at a rate of basically one person will take 12 seconds. It's little wrong here, because a single person is still taking 1 minute, but I will have one person coming out of the queue every 12 seconds. So, you now see the speed at which your queue will move, right. So, earlier one person was taking 1 minute in this scenario. Now, we have basically every 12 seconds one person is coming out of this queue. So, this concept is nothing but pipeline. So, what you have done, you have let me try to draw it more clearly. Okay. So, so earlier okay. So, earlier basically there was one table, a person was coming, he was taking the food, he was taking 1 minute, and I could serve one person per minute. So, this was my rate of serving in the mess, all right. All right. So, one person is getting served per minute. Now, this whole task which takes 1 minute is divided into 5 small segments. All right. Is it 5? Oh, I have drawn 6. Okay, I think it's even better because we are taking this example of 1 minute. So, 60 second divided by 10 second divided by 6 is better. So, here let me denote these persons as 1, 2, 3. So, this is my queue. So, this whole task still take 1 minute, but now this each segment takes 10 seconds. So, 10 seconds, 10 seconds, 10 seconds, and that is how we get 60 seconds. Now, what we are saying? So, we are pushing, or the people are moving into this queue. So, the first person moves here, all right. So, let us say this is our time scale, this is how time is increasing. So, on we start from 0 and time is increasing in this direction, all right. So, on the first 10 seconds, this first person is in this window. So, when we are done with first 1 second, this guy who was in this window, he moves here, right. So, after 10 seconds, this guy moves here. Now, what happens in the same duration? This time slot is now empty, or this counter. So, these are all you can imagine for visualization. You can think of these are you are walking through a buffet, and these are different items which are kept there. So, as the first person moves to the second counter, the second person will move to this counter now, right. So, let me draw this in this way. So, this is my first person. So, he is in the, so let me number them. So, this is A, B, C, D, E and F. So, these are my 6 stages of food counters. So, the first person, he in the after 10 seconds or first 10 seconds he is here. In the second 10 seconds he is in counter B, all right. So, So, this is first person and his state or in which counter he is in, I am writing it here. So, he is in counter A first, in counter B in next 10 seconds, counter C, D, E and F. So, after 1 minute he is out of the queue, after 1 minute. Now, look at this second guy. Second guy, after this first 10 seconds, this counter A is free, so he moves to counter A when the first guy moves to counter B, alright, and then he moves to, like when the first guy moves to counter C, he moves to counter B and so on. So, C, D, E and F. So, basically you see that after 1 minute this guy came out of the queue, after 1 minute 10 seconds the second guy came out of the queue. What will happen to the third guy? So, third guy, when this second guy moves out of counter A, he occupies that counter and so on. So, it is nothing but some kind of a pipeline. So, you have a pipeline, people enter the pipeline and the next guy follows him and you move from one counter to another counter. The next guy basically is only offset by certain delay, but he also follows you and so on, right. Now, with this thing we can now serve one person in 10 seconds. So, you see that I have achieved significant performance because I have divided this big task into smaller chunk of task, and as I move from one task to another, basically the task which is free, I will assign a new task there. So, all the assembly lines in car manufacturing, automobile industry, you might have seen that they work in using the same principle. So, basically you whole task of automobile engineering or basically designing a car is segmented into multiple tasks. So, the car moves, or the car which is under development moves from one segment to another, and then the new car or new vehicle comes in that place and so on. Okay. Anyways, to coming back to this analogy of our mess. So, now the organization of the mess will determine whether I will implement it in this way or I will implement it in this way. So, you remember my architecture or ISA only talks about the broader things, like whether I will be able to serve veg, non-veg, how I will handle different things, etc. Theoretically it says that. But when I actually come and implement the mess or build the mess, I have to look at these design decisions. So, how many people will, or how many counters I want to make, whether it will be a single counter, whether I will have multiple counters. So, now in this case, if I have multiple counters, I will need more resources, I have to spend more money, but I will get better performance. Whereas, if my requirement is such that I can live with this, it will be much cheaper and it might solve my purpose. So, you see that here the organization is different, but the architecture is same. Does this make sense? All right. Now, what else the architecture talks about? So, this is what we mean by pipeline depth. So, I can divide this whole task into six smaller tasks. I can divide it into even higher number of tasks. Let us say I can divide it into 12 small tasks. In that case, I will have better speed, because now maybe now every 5 seconds I will have one person serve, right. But there will be the other constraints, like you will have more resources required if you want to divide into 12 subtasks. Now you have to also think about it, like do you have 12 items to serve, because just for speed you can't keep on dividing this into multiple counters, because that might not lead to performance if this is not going to be addressed. Now there is another aspect which we can think of. Let us say I am designing a mess where there are a lot of students come immediately when the lunch time starts. Now, so you can think of that, okay, I can have one this kind of counter, then I will be able to serve one person in 10 seconds. Now if this is not enough for certain application, you might have to think of even higher performance. So how can you think of about higher performance? So you can say that, okay, I will have multiple such pipelines, I will set up multiple counters on the mesh. So basically try to visualize, that is why I am trying to bring forward this mesh analogy time and again. So now I can say that, okay, I will have two such counters operating simultaneously, all both of them are identical, has 6 stages and so on. Now what I can do, I can form two queues, right. So one queue for this, one queue for that. Now what is the advantage? Now I can serve one person every 5 seconds, right, because now I have doubled my number of pipelines, all right. So this is, so we talked about pipeline depth. This is, so pipeline depth is how many stages the pipeline should have. So basically whether it should have 6 stage, whether it should have 12 stage, whether it should have 3 stage and so on. So okay. So this is pipeline depth, the number of pipelines. So number of pipelines, the analogy is basically how many simultaneous counters you want. So number of pipelines. Now we can try to find further analogies. For example, let us say, okay, maybe to understand that we have to change the problem slightly or change the analogy very in a subtle way. So let us say you are in a mess or in a buffet where some items are being prepared at that time itself. So for example, let us say some fries or maybe some roti etc. being prepared. Now so the guy who is preparing, let us say the roti in one of the stages. So let us say in this stage roti is being prepared. So an analogy to this could be your execution stage. So in a computer, actually there are different stages through which an instruction goes through. Let us assume that the analogy here we are trying to make is basically the roti making analogy is corresponding to the execution stage, but yeah, it's not very important, but yeah. So in this stage roti is being made. Now one scenario could be that this guy serves only one roti to one person. So every time this person comes here in this stage, this guy looks at it and he starts making the roti. Now he has the dough for one roti, he makes the roti, he starts frying it, and then he gives it to him. Now think about a situation where every time he is done with the roti making, he has to rush to the store and gets the dough to make the new roti. So if that is the case, then this step might take quite significant amount of time. So he makes the roti, he rushes to the store and gets the roti back. Now another thing here interesting, and maybe I am jumping a bit. So let us say this stage in that case takes more than 10 seconds. Then you have to slow down all your stages also, because if this stage is taking 15 seconds, though 15 seconds, then what will happen? The guy who is in this stage, he will move to the next stage after 10 seconds. So this stage is empty now, but since this guy has not got his roti, so he will be waiting here and he will not move forward. So your pipeline will be basically not efficiently implemented. So to overcome that, most of the RISC processor, what it does, it looks at the stage which takes maximum amount of time, and that stage determines what will be the speed at which your information will move in the pipeline, or in this case the person will move in the pipeline. Alright. So if this stage takes 15 seconds, so every stage will be basically slowed down to 15 seconds. The other option can be, let us say you divide this stage into two stages. In either way you are basically compromising with your performance. Now how to address this issue of rushing to the store and getting the roti? So one possibility could be, you give him the dose which he need, at least you constantly supply it, so that he does not need to rush every time a new person comes. So the appropriate analogy I am trying to establish here is, let us say this is your main memory, alright, and this is your cache. So cache is a small memory where you basically can bring something and keep as a copy, and whatever you need to do, you can easily access them and get the work done. So basically if you give that person, the roti maker, some stock of the dough locally, then he does not need to rush and get the dough every time, and that way maybe you can get this work done in 10 seconds and you will get a better performance. But of course it requires resources. So basically you will need extra utensils, etc., to keep your raw material here, and you might also need to have some plan to replenish this time to time. Alright. So this is what cache is. Now you can implement without all these things, still your ISA remains same, but with cache you can improve the performance. The other things, so basically this is what we discuss as cache. Whether your the microarchitecture will decide whether you will have cache or no cache. The silicon area. So basically silicon area can be thought of as the floor size of the mesh. So basically if you have a good amount of real estate, then you can plan this several things or maybe multiple counters etc. on the mess floor. But if you do not have that much space, then you will not be able to put, let us say, multiple counters and so on. So, basically how big you want to make this establishment. So, that is also defined by microarchitecture. All right. The other things like how much resources you want to spend. So, basically if you have these multiple counters, you will need more manpower to deal with it and so on. So, you will need more money, and if we can basically you can if we can bring an analogy for money and the power in the chip or energy consumed in a chip, then basically the more amount of resources you put in, you will be burning more and more power. Now, there is some other interesting things. So, silicon area, power, etc., the equivalent we have already discussed. The other interesting things can be, let us say, out of order execution. Now, what do we mean by that? So, so I can define a protocol where everybody needs to go in the same queue. All right. Now, it might happen that let us say in this case the customer or this guy, he is not interested in taking roti. All right. So, while this first person is waiting for his roti and this guy says that I do not need a roti, do we allow him to jump the queue and move ahead of the first guy? This is what is called basically your execution order, or you allowing out of order execution. By default, you always only allow in order execution. So, even if this guy does not need roti, he has to wait, and once this first guy moves to the moves to this counter, then he will be just waiting in this counter, though he will not take roti, and then only he can move ahead, basically following the first person. But if your system for achieving better performance, because if you can move this guy ahead, then you will save some time and you can serve the other persons more faster. So, whether you will allow this thing to happen or not, that is also defined by the microarchitecture. All right. So, the broad theoretical definition of the mesh will not include all these details, but while implementing you may or may not have this thing. Now, of course, if you allow out of order execution or if you allow the person to jump the queue, you have to have enough checks and balances so that nobody basically it does not create a chaos, and that is why you need more resources. So, all these things are very interesting to look at. Similarly, there is other things like bus width, or let us say ALU width. So, these things are also defined by the microarchitecture. So, what will be the equivalent analogy in our example? So, so again these are very so bus width means the amount of data that can move. So, basically let us say I have 4 parallel lines, these are called my bus. So, even if I have 8-bit data, if I have 4 parallel lines, okay. So, let me write down Yeah. So, I have 8 parallel lines and I have 8 bit data. So, I can basically I can transmit the data in one clock cycle from one node to another node, because I have a bus which can transmit all these 8 bits at a time. But it let us say I have now 16 bit data, but my bus width is still 8 bit. In that case, what I will have to do? I will have to break this 16 bit into 2 parts. I will be sending the first part in one go and the second part in another go. So, basically this is what we understand by bus width. Now, what could be the appropriate analogy in our mesh case? So, let us say the serving spoon kept here in these counters are nothing but your bus width. So, I can keep a very small serving spoon. In that case, what will happen? In that case, the guy has to take multiple times, right? So, basically if your bus width is very small, then you have to do the job multiple times and it will take more time. Now, the advantage might be the small spoons might cost you less, and so you will save some money, but it will affect your time, because the guy each guy will be taking more time to take their food. So, that roughly can be compared with your bus width. Or on the other hand, you can have a big enough spoon which basically anybody can take a single serving, and that should be enough. Alright. Sometimes the spoon, if it is so big, then maybe some people will only take half a spoon. So, there you will be putting more resources, but you will be underutilizing that resource. Similarly, the other term which we have discussed is Alu weight. Now, the analogy again, we can come back to this roti maker here. So, let us say I have I can employ 2 people here who can make 2 rotis at a time in the same time. So, in that case, let us say in general or on an average, every person takes 2 rotis. Then this execution can be made faster compared to the case where there is only one roti maker and he is trying his best to make those rotis. But if every person is on an average taking 2 rotis, then he has to make 2 rotis for each person and it will take more time. So, if you have a wider ALU which can handle, let us say 64 bit at a time, then it can get the execution done faster. And the analogy here will be, you have multiple roti makers, they are making all the rotis that are required by a person and is providing that. Whereas, if I have, let us say a 8 bit ALU and my task is 64 bit, then I have to do this task here 8 times to get the final result. Similarly, the analogy here is basically if every person needs 2 rotis and I have one person, then he has to make 2 rotis and we have to wait till the roti is made. So, I hope with this analogy we could highlight the difference between ISA and organization. We could also highlight the different aspects of a computer microarchitecture, especially the at a very crude level. We got some idea about what pipeline is, what the depth of pipeline means, and the number of pipelines in a processor. We also very through crude examples we looked at the usefulness of cache, etc. We also talked about out of order execution, bus weight, ALU weight, etc. So, of course, we will go into these things when we talk more about processor design, or the second part, basically when we talk about the microarchitecture in more detail. and there we will talk in more detail about each of these design decisions. Now, one thing I want you to take away from this is that we are here conceptually trying to understand the difference between ISA and organization. And just to reiterate, ISA talks about the theoretically what the program is supposed to, or what the programmer is supposed to expect from the architecture, or basically a very theoretical description about the machine where the program will run. It provides you the details about the kind of memory, the kind of register it will support, the kind of instructions it will support, the interrupts, how it will be handled, input output and data types, etc. But actual hardware implementation is defined in the organization, and that design decisions are made based on different aspects like the speed, the required speed, the kind of cost you can you are okay to bear, and things like that. We also looked at the nitty-gritties or examples of microarchitectural decisions like pipeline depth, number of pipelines, cache, silicon area, peak power, execution ordering, bus width, ALU width, etc. All right. So, very quickly I would also like to highlight or give you some examples of architectures where basically real life examples of same architectures but different microarchitectures, same ISA and different microarchitectures. Examples are basically here we can see AMD Phenom X4. So, this processor is a x86 ISA processor. Similarly, Intel Atom is an x86 ISA processor. But you see the kind of difference in microarchitecture in these two implementation. So, one is a quad core consuming 125 watt of power. So, pretty beefy processor consuming lot of power, etc. Whereas the Intel Atom is a primarily designed for handheld devices. It is a single core burning only 2 watt of power. Basically then it also highlights how many instructions in parallel it can decode. So, basically the AMD processor can decode 3 instructions per cycle per core. So, basically what it means that the AMD processor has as if the 3 pipelines, parallel pipelines, which can basically decode or which can handle 3 queues at the same time, whereas the Atom has 2 such pipelines. So, that is why it can decode 2 instructions per cycle per core. The L1 cache or instruction cache is 64 KB. It also has 64 KB data cache. Similarly, the Atom has 32 KB L1 cache and basically 24 KB L1 data cache, and instruction cache is 32 KB. Surprisingly, the L2 cache is same 512 KB for both the processors. The AMD processor can support out of order execution, whereas the Intel is not supporting that. It can operate at 2.6 gigahertz, significantly faster than 1.6 gigahertz by the Intel Atom. Similarly, we can quickly look into another example where both the microarchitecture as well as the ISAs are different. So, we are keeping the AMD Phenom X4 from the previous slide. Now, if we look at the IBM Power 7, so it uses the ISA Power ISA. It has 8 cores, burns 200 watt and you see that it decodes 6 instructions per cycle. The cache sizes are mentioned, and the L2 is little smaller here, and this also can supports out of order, and it can run much faster, 4.25 gigahertz. So you see that there are different ways the processors can be designed. There can be multiple ISAs or same ISA, different microarchitecture and so on. All right. So, I hope this discussion adequately answers or adequately highlights the difference between the ISA and microarchitecture, and going forward basically we will be looking into some more details about ISA and the differentiating factors, how ISAs are designed, etc., before we move on to the assembly coding or basically arithmetic part of it. All right. Okay. So, I will pause for questions if there is any. Thank you.